Assalamu alaikum أصدقاء الطلاب. Welcome to Chemistry Online with Mr. Ahmed Soliman. Today we are starting lesson 2 of chapter 4. Lesson 2 is talking about the structure of nuclear atom. The scientists determine the structure of the atom, or we can say what inside the atom, by using experiments. As you know, in the atom we have something called subatomic particles. The atom has nucleus containing proton carrying positive charge, neutron, neutral, and the electron outside carrying negative charge. So we have three kinds of subatomic particles in the atom. As we said before about Dalton's atomic theory, he accepted something from Democritus and add more than that. Also, what scientists came after Dalton accepted some of his ideas in the theory. One of the things that changed from the theory of Dalton, that atoms are now known to be divisible, not indivisible. Atoms can be divided now, so they changed the idea of indivisible atoms. They can break these atoms smaller and smaller, and they found something called the subatomic particle, as I said. So some ideas of Dalton are changed. As I said, we have three kinds of subatomic particles: electrons, protons, and neutrons. First, let's start by the electrons and how can they discover the electrons. English physicist Thomson, he's very famous, discovered the electron. Electrons are negatively charged subatomic particles, as you know before. Thomson did an experiment, or performed an experiment in many steps to find out what something small inside the atom, and he discovered the electron. He used in his experiment kind of gas, or many kinds of gases, in low pressure, and by using the electric current, he allowed this electric current to be sealed in a gas inside a tube. I will show you the device now, and put at the two ends of this device discs like this and like this inside the tube. Okay, and allow electricity to move from here to there with very low pressure of a kind of gas inside. Okay, and connect these two ends with electricity, and they call them electrodes, negative electrode and the positive electrode. The electrode were connected to source of electricity. Look, this is the metal disc, negative electrode, or we can say cathode, and this is the other disc, metal disc, with connected with a positive electrode, or we can say anode. Inside the tube, kind of gas with very low pressure, and we have here vacuum pump to allow kind of gas to enter or to take out any air inside first, then put some kind of gases inside the tube, and connect these two discs with very high voltage. So the voltage is very high, but the pressure of the gas is very low here. Don't confuse. And allow the electricity to move from this end to another end. What happens here? Because this end has this negative or cathode, he found a beam of charge transfer from this end to another end. This beam called cathode rays because it emits from negative or from cathode electrode. So he called it cathode rays. And these cathode rays are negative because they emit from negative electrodes, so they are negative. Okay? And because the charge are negative, he discovered that the electron is carrying negative charge, and this beam formed from many of these electrons. This is the result he found. And he can see that because it was glowing beam, in the form of beam, glowing beam. And he called it cathode rays, as I said before. Okay, that transfer from cathode to anode is the result of the experiment. Thomson found that these rays, or this beam of cathode rays, is deflected by electricity. How come? He put positive plate here and negative plate here and allow this beam to move. It didn't move in a straight line as the previous step, but it moves direction to the direction of positive. It means it's what? It's negative, because it moves toward the positive. He changed the position of the plate and put the positive here and negative here. He found the beam moves like this. It means it deflected toward the positive, so it's negative. He confirmed that these particles in the cathode rays are negative, which are the electrons. So the cathode rays deflected by electricity charged metal plate. Okay. Electrons moves at high speed. It's very, 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 very fast. Thomson called these particles not electrons at this moment. He called this particle corpuscles. Corpuscles is the name, the old name of electrons. Later they called it electrons after that. Also, he tested the effect of magnet to this beam. He found it's deflected as well. It's affected by magnet. Cathode rays can also be deflected by magnet. Look, the beam, what happens here when he approached the magnet, when he put the magnet here, the beam deflected like this. So it's affected by magnet, not by electricity only. And also, he could measure something else. He needed to measure the charge of electron. This electron he discovered, he need to measure the charge, how many coulombs this electron. But he couldn't. By some equations, he could find out the ratio between the charge of the electron and its mass, E over m. By his experiment, he measured the ratio of electron's charge to its mass, E over m only. But he couldn't measure the charge only, which is now known as 1.6 times 10 power of negative 19 coulomb. But he didn't measure this. He was planning to measure it, but he couldn't. But from his equation, he measured the ratio between this charge and the mass. That's what he achieved in his experiments. And he found this ratio to be constant, as I said. Electrons formed in his experiment were the same even you change the gas inside the tube. So the electrons didn't depend on the kind of gas, the tube, and also didn't depend on the type of the metal used in the electrodes, metal discs, okay, with any kind produce the same electron. Electrons are the same for any case of this. From all of that, Thomson concluded that electrons are a component of atoms, but not only the only component. It's one of the components of the atom in all elements. Let's see Thomson's experiment in this video.
This is a cathode ray tube. This is the anode, and this is the cathode. It's hooked up to an electric current, like I'm about to do here. You can see a beam moving across. You might think it's light, but when you take a magnet to light, does it do this? You can see that it's bending or deflecting away from the magnet, so we know that it's not actually light. And that the piece of the atom that he was seeing was negative based on the end of the magnet that was causing a repulsion.
Millikan is a scientist, came after that, and he measured the charge of the electron, which is 1.6 times 10 to the negative 19. He could measure that. He find out the quantity of the electron's charge by experiment called oil drop experiment. What did he do? Look. Millikan put some oil droplets inside a cylinder like this, and make microscope here to see what happens inside. And from this side, another side, allow the electrons to move from this side. This side has electrons to move, and here allow some droplets of oil to fall down. When the droplets are falling down here, it moves by the effect of gravity toward the bottom. By allowing the electrons here, it hits, or they hit these drops. Some of these drops carry negative charge. Now, not all of them, but some of them. He put here positive plate and negative plate here to control the movement of the droplets carrying negative charge here. Okay, so imagine that if you have negative charged droplet here and you turn it on the plate which is positive here in this position, it can attract the negative charge here and make the droplet not moving down toward the earth by gravity, but move up or slow down or even stop by controlling the plate of positive here. It means he controlled the movement of the droplet by using very complicated equations containing the velocity of the droplets and the mass and many variables. He found the value of the charge, which one of the variables in the equations, the charge of the electron. But he found something. He found the results are different each time. He repeated the experiment and he found the result each time something else. Here value, here another value, here another value, and so on. Each time has value different from the other one. What does it mean? It means the experiment is broken, it's failed. No, he still thinking about these values he got. Imagine with me, if you have value here, imagine with me, the value here is 2, here 8, here 6, here 12. Imagine that, يعني. It was more complicated than these values طبعا. But imagine the values are like this. What does it mean? It means this 2 means 2 times 1. This 8 means 2 times 4. This 6 means 2 times 3. This 12 means 2 times 6. It means the least one of them is this. It means this droplet of the first experiment is only 1 electron is carried on this droplet, 1 electron, and the value of the charge is 2 at this moment, for example. يعني. It means the value of the electron charge is 2, but here there were 4 electrons, not only 1. Here 3 electrons on this droplet, and the value of the charge is 2 as well. Here the droplet has 6 electrons, times 2 makes 12. It means this repeated number here is the value of the charge. The number was very complicated. This 2 is not 2, it was 1.6 times 10 power of negative 19 times something here, times 1, times 4, times 3, times 6, and he found the least number here. He found 1.6 times 10 power of negative 19. This is the value of the charge of the electron. He found that after thinking, and it was correct. They found the science after that, it's correct. From those, he measured the charge of the electron that Thomson couldn't do. Okay. From this conclusion, look, this is the value of the charge from his experiment. Also, because he has the ratio E over M made by Thomson, okay, and he measured the charge of the electron, it means he could measure the mass as well. This is known, so he found the missing value. That means Millikan could measure the charge of the electron, and also he measured the mass of this electron. Let's go to Millikan experiment.
Millikan's oil drop experiment. British physicist J.J. Thomson had measured the ratio of electrical charge to the mass of an electron using a cathode ray tube in 1897. Later, R.A. Millikan looked to determine the charge on the electrons. The famous method that he devised between 1906 and 1914 to measure the charge E of an electron is known as the Millikan's oil drop experiment. Using this method, he calculated that the charge on an electron was about 1.6 times 10 power negative 19 coulombs. In the Millikan's oil drop method, an atomizer produces oil droplets in the form of mist, which are sent through a plate of electrical condenser. There are different forces which act on the oil drop, including gravitational, electrostatic force due to electric field, and the rate at which these drops fall were measured by observing them through a micrometer eyepiece of a telescope. X-rays were passed through the chamber to ionize the air inside. On colliding with gaseous ions, these oil droplets acquire charge. The rate at which these droplets fall can be controlled by changing the strength of applied voltage to the plate. With this experiment, he observed that the magnitude of electrical charge Q on the droplets is always a multiple of electrical charge E. That is, Q is equal to Ne, where N is equal to 1, 2, 3, and so on. Using the value of charge of the electron, the mass of the electron, Me, was then determined by combining Thomson's value of E by Me ratio. The value shown is the value of the mass of an electron.
So Millikan found the quantities that were mysterious for the previous scientists. The electron has unit of negative charge as 1 over 1840 of the mass of hydrogen atom. Why hydrogen atom? Hydrogen atom has one atomic number and one mass number. It means it has only one electron and one proton. It doesn't have any neutron. One proton and one electron without any neutrons. This is a hydrogen. Electron mass is negligible. Okay. But protons, only one here. So the mass of hydrogen, we can say that the mass of hydrogen equal the mass of one proton. So if you want to say the mass of one proton equal the mass of one hydrogen atom. To imagine the mass of the electron is 1 over 1840 of the mass of the proton, or we can say of the mass of hydrogen, If you put 1840 electrons together, it makes one hydrogen atom, or the mass of one hydrogen atom. If you put 1840 electrons together, it means only one equal one hydrogen atom mass or one proton. It means much smaller. The electron is much smaller than the proton. This is the electron. What about protons and neutrons? Look, you recall the experiment of Thomson? Because we have cathode electrode here emits the electron as beam, that means the other part has positive electrode or anode, also emits like charges, but they are positive because it emits from the positive part, so it's positive. The cathode rays are electrons, yes, we said that, ماشي, and it give off atoms, remaining the atoms that have lost the electrons, but hydrogen losing electrons, and the other part can emit protons. They thought about that. We have some ideas, 4 ideas about that. We can think that ideas about matter and electric charge. Atoms have no net electric charge. It means they are neutral. Atoms are neutral. What does it mean? It means the number of electrons negative in the atom equal exactly the number of protons positive. Equal in their numbers. And neutrons already neutral. So from this we can say no net electric charge. يعني الcharge neutral or electrically neutral in the atom. The atom are electrically neutral. Electric charges are carried by particles of matter. Yes, the charges are carried by particles of matter like oil, I explained, مثلا, for example. Electric charges always exist as whole number. We cannot find half electron or half charge negative or quarter positive, nothing like this. Must be whole number. No traction of charges. يعني. Number 4, if you have number of negatively charged particles combining together, they equal the positive charged particles, as I said before. So the negative charged equal the positive charged particles. It means it's electrically neutral, as I said before. They are the 4 points or the 4 ideas about that. From those, we can say that 1 unit of positive charge should remain when typical hydrogen atom loses an electron. 1 unit of positive charge should remain when a typical hydrogen atom loses an electron. Because when hydrogen loses its electron, the positive charge is still hydrogen is 1 electron, 1 proton, and has no neutron. So if the electron is moving, the positive charge is still here remaining in the hydrogen atom. طيب, how did they discover the protons and the neutrons? We have a scientist called Goldstein, or sometimes Goldstein. Okay, Goldstein observed this cathode rays tube, as I said before, and he found that in the opposite direction of cathode rays there is another rays but positive, and he said that must be these rays composed of protons which carrying positive charge. Goldstein observed these cathode rays. Also, I said he concluded that it's composed of positive particles as well. So these positive subatomic particles called protons after that. We have another scientist called Chadwick. Chadwick came and confirmed the existence of electrons and protons, but he said we have the third subatomic particles called neutron. And these neutrons are neutral. Neutrons are subatomic particles with no charge, but with mass. It has mass, and its mass equal to the mass of protons. Listen, the mass of protons equal the mass, almost the mass of neutrons. But protons has charge positive 1, neutrons has no charge, positive with negative like this, no charge. Okay, don't confuse. Look at this table to summarize all of this information. Electron has a symbol E small, proton B small, and neutron N small. You can make like 0 here, or we can make N positive with negative like this. Okay, these are the symbols for each of them. What about relative charge? Relative charge is negative for electron, negative 1. Proton, positive 1, but has no relative charge for neutron because it's neutral, 0. But we have something called relative mass, not relative charge, and also actual mass, and also actual charge. Look, the actual charge different from relative charge. Relative charge first, let's see this first. Relative charge is the charge of the electron relative to proton. The electron relative to proton as charge equal 1 and 1, but this carry negative and this carry positive. Don't confuse. Listen. We have electron. The electron has charge 1.6 times 10 to the negative 19. This is not relative, it's called actual charge. And the charge of proton, the same, the charge, I'm talking about the charge now, not the mass. The charge of proton, 1.6 times 10 to the negative 19. So 1 of electron equal 1 of proton as charge, but this is negative and this is positive. We called this value relative charge because it's explaining the relationship between them. 1 to 1, they are equal. But if you need the actual charge, this is the actual charge, or this is the value of the charge. That I'm talking about the charge now. the mass of electron is very, 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 very small compared to the proton. The mass is very small compared to the proton. Okay? How many? One electron equal, as I said before, its mass. Now I'm talking about mass, not charge. 1 over 1840 of the mass of proton. As I said, this is the mass. But if you want to compare between the mass of protons and the mass, not charge, of neutrons, they are almost equal. But they are not equal in their charges. Protons carrying positive charge and neutrons no charge. So don't confuse, please. Here I'm talking about the charge. The charge of electron equals the charge of proton. The actual charge. And the relative charge is 1 negative here, 1 positive here. The mass of electron and proton, here electron is smaller, not equal بقى. Smaller than proton. How many? 1 over 1840 of the proton. But what about the proton and the neutron? Their masses are equal, but their charges are not equal. This is positive and this is neutral. Back to this table again. Look, the relative charge here I explained. Relative mass is 1 over 1840 for the electron. Okay? But because proton equal the neutron in their mass, so the relative mass is equal 1 and 1. But look at the actual mass. Here, equal here for proton and neutron, but not equal to the electron, because electron much smaller than those of proton and neutron. Look, this 10 power of negative 24, but this 10 power of negative 28. Very, very small. Okay, so this is the masses. The scientists found that the nucleus inside the atom composed of protons and neutrons, as I said before, and we have some smaller subatomic particles other than protons and neutrons. They called it quarks, and we have positive quarks and negative quarks. These quarks are transferring from neutron to proton, from proton to neutron, and so on. They called it quarks. Atomic nucleus. How can you describe the structure of a nuclear atom now? The nucleus composed of protons and neutrons, as we said before, that discovered by the scientists. When subatomic particles were discovered, scientists wondered how the particles were put together in an atom, how they are in the atom all together. The scientists thought that electrons distributed. Before that, it was wrong. They said that electrons are distributed throughout the atom. Imagine that this is a model, and this is the atom, and electrons are distributed like this. No nucleus ولا أي حاجة. Okay? They thought that, and uniformly with positive charged materials. And this material, they imagine that are positive. The material of this atom is the positive part. Okay? Like this. This is one of the models. Thomson put this atomic model, and they called this model Plum-Pudding model. So if I ask you, what's the name of the Thomson atomic model? Plum-Pudding model. They imagine that what I said, imagine that one of the positive charged particles, مثلا, for example, like raisins in a muffin or dough, okay, like muffin like this, and this one of the charge, and the raisins inside the other charge, like I explained in the previous slide. Thomson worked in this, and Rutherford came after that, and got a Nobel Prize because his experiment he discovered or he improved the model that similar to what accepted today by his experiment without seeing electrons or any subatomic particles. Rutherford, with some other scientists, tested the existence of plum pudding model of the atomic structure, and he discovered something else. He used something called alpha particles, and he used helium atoms to take this alpha from it, alpha carrying positive charge only. How? Let's see this experiment of Rutherford. He put this source of alpha particles like uranium, like plutonium, whatever, here, and put it in a lead shield to allow the rays to move in this direction only, not in any directions here. Lead prevents any of rays to get out from any side, only this side that has opening. Lead shields here does this. Here alpha particles which carrying positive charge, and he prepared this metal sheet, which is incomplete metal sheet here, and make this gold foil. Gold foil is a substance that composed of atoms. He want to see what include inside the atoms. He found the metal like gold to see what atoms inside and what's the structure of the atom inside. Also, he will allow these rays to move, but we cannot see these rays if it hits the gold, deflected or reflected or transferred. How can we know that? He plated the inside part of this metal by substance that make glowing when these rays hit it. It makes it glowing, so we can discover if the rays here penetrated this gold and move here, or deflected or reflected or whatever. Okay. What happens in this experiment? Let's see. First, he allowed the rays to move in this direction, which alpha positive, and he found that some rays are reflected like this, some of them are penetrated but deflected like this, and majority are penetrate and move in straight line like this. Majority of them. 3 observations. What does it mean? It means when the rays are reflected like this, it means positive hits something here in the atom. Look. Imagine with me, this is atoms. When the rays are moving and reflected like this, it means it hits something massive. Like this. It moves like this, and that's what happened. Like this. It's reflected. It means something massive here inside the atom. He said so. The atom has something massive at the middle. Others move like this. Look. And deflected like this, because he found spots glowing here. Deflected, but not a lot. Okay? What does it mean? It means some rays are moving, but move like this Because it rebels with something here. It rebels. And because this alpha is positive, so it rebels with something positive. So the massive part at the middle, which is known as nucleus, carrying positive charge. So first he found something massive here, which is a nucleus at the middle, and it's massive. Also he found that this middle part is carrying positive charge. The third observation, these rays, majority of them penetrated and move in a straight line. What does it mean? It means the rays are moving without any hitting, or like this, like this, like this. What does it mean? Like this maybe, like this maybe, and so on, like this. It means in the atom, most of the atom is empty space. Nothing here to hit the rays when it moves. It means the atom has empty space in most of it. 3 observations, and he concluded 3 results. You can imagine that. Okay, it means he found this model, which is not lump budding model, and the electrons spread throughout the atom, but he found that something massive at the middle, and this is carrying positive charge at the middle of the atom, and most of the atom is empty space here, nothing here, empty space here. And this is very similar to the model accepted today. Not exactly, but يعني similar. Okay, so according to this theory, that's what he got, okay, due to this observation. Look, to imagine what I explained, some of them reflected due to something massive here. Some of them deflected, not reflected, deflected due to the repulsion between this positive alpha and the positive charge in the nucleus. Must be positive, you need to repel. And the majority are moving in a straight line like this. Look, 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 look. It means here empty space. Look here again. Empty space in most of the atom. Look at this also. Most of the atom is empty space. He concluded many things from this experiment without seeing the atom or the structure of the atom, but he concluded the model of the atom. Let's see the video of Rutherford's experiment.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So Rutherford model is similar to what accepted today, but not exactly the same, but improved from the previous models of Thomson. Improved. As I said, he said mostly empty space of the atom. The atom is mostly empty space. And also he said that the lack of deflection of most of alpha particles due to the massive part inside, and also the positive charge carried by the nucleus, positive charged of the nucleus, and it has mass concentrated in this small region which called the nucleus afterward. Rutherford's model, known as nuclear atom now, after that. Why? Because he discovered the nucleus and the charge of the nucleus, which is positive. So they called it nuclear atom for this reason. According to this model of Rutherford, nucleus is tiny and densely packed or compared with the atom as whole. Yes, it's very, very small at the middle or at the center of the atom. Imagine that if the atom has size as the football stadium, the nucleus will be about the size of marble. You can imagine that if you have a stadium, okay, this is the size of the atom, the marble is the size of the nucleus. Rutherford atomic model turned out to be incomplete because he didn't explain the chemical properties of the element. So they call it's incomplete. This is the story of discovering the structure of the atom, and this is the end of lesson 2. I hope to understand everything. Thank you, Shabab.